All right, hi there to everybody watching the recording here. Wanted to start off today by doing one more example from chapter 11, and then we'll jump into chapter 12. So this will be kind of a review of what we did on Monday, and then we'll jump into um, automata theory, which is my favorite part of this class. So it's going to be fun. But let's do one more example first of the big O notation. And what I wanted to discuss was an example of the computation of polynomials, right? Okay, so a polynomial, as you probably know, is a sum of coefficients times powers of x, right? So it looks something like, 4x squared plus, x minus 5 or something like this, and that's a polynomial. And if we wanted to make this a little bit more abstract, maybe we could say, it's, coefficient of some coefficient times, x to the n. Maybe we'll call this the nth coefficient, right? C sub n plus some n minus first coefficient times, x to the n minus 1 plus yada, 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 plus the first coefficient times x plus the 0th coefficient, right? Which would be, times x to the 0, but usually we don't write that, yeah? And if we wanted to write this in terms of summation notation, right? This would be a sum from I equals what? Where are we going to start our summation here? Yeah, there we go. From 0 to n of c sub I times x to the I. Very nice. Okay. And I want to talk about how to compute one of these guys, right? So if I had a function that was going to compute this thing, right? Well, my function would have to be a function of, maybe it would be a function of 2 arguments. Maybe we would have an array of coefficients and then our value of x, right? So maybe we would have, double array of c, and there would be n of those, right? And of course, our value of x, right? So this would be, and x could be a double as well. I guess I should have given a type on there, huh? Let me say double x. So if I was going to, sketch this out in C++, how would this work?
Hey, sorry, just to ask real quick, should your function also take an ending n?
Yeah, I suppose so. Well, let's say n is a global constant, right? Maybe here, let me do this, right? Because it's got to be a constant in order to be my array size. So let's say we have a global constant called n. How about that? Make it a capital N just to indicate that it's a constant there. But yes, you're absolutely right. We would need to know the value of n. Absolutely. Yeah. So what do you guys think? How would this work? Okay, so we'll have a for loop, right? For int I equals 0, I is less than n, I plus plus, and I'll have some sum variable. I guess I should probably initialize my sum to 0, right? Put that up there. And my sum, as you said, plus equals C of I. Let's not do a curvy I. Let me keep my handwriting consistent here. C of I times x, and then the sum is declared outside the for. Oh yeah, that should be outside the for loop. Yep, which it is. Yep. C of I times x. Well, yeah, I think we're going to need, the power of x to the n minus I, right? power of x. And so if the I is at 0, would we want x to the I or x to the n minus I? Which way would those go? Just I, right? Okay. And, and then at the end, we would return our sum. Okay. And what I'd like to do now is find the runtime of this algorithm, of this function, right? In terms of our big O notation, right? So how would that work? This will be my first function. I'm going to do this 2 different ways, and we're going to come up with 2 different computations for our big O notation here. But so this is the first one. This is what I would call the naive approach, right? Which means the first obvious idea, right? It depends on how the power function is implemented, sure. And so if again, we use the naive approach for our power function, right? How would that work? How many multiplications would we need in order to, achieve our, finding the power of x to the I? I multiplications each time. Yeah, very good, right? Because if we wanted to do, x cubed, we would have to do x times x times x, right? So there would be, I guess it would be I minus 1, but again, we're not worrying about those minus 1s with that big O notation, right? So it would be, I multiplications for each loop, right? So if I wanted to compute the total number of operations here, there's going to be quite a few things going on. We're going to be doing multiplications inside of POW. We're going to be doing multiplications here. We're going to be doing additions here, and we're going to be doing comparisons here, right? So let's count up each. Let's do comparisons, additions, and multiplications. And let's count up how many of each of those there are, right? So how many comparisons are we going to do in this algorithm? The comparisons, by that I mean the less than, right? Yeah, we'll do n of them, 1 for each time we go through the loop. Okay, how many additions are we going to do? And same deal, right? Because we'll do 1 per loop. But what about the multiplications? That's where it starts to get interesting. Yeah, the sum of I, right? So this is going to be the sum of what? So we're going to start off I at 0, right? Yeah, sum from I equals 0 to n of I. Excellent. And how much is that according to Gauss's law? Good. N times n plus 1 over 2. And so our total here, I guess I should have used a capital N, sorry. There we go. So our total here is going to be 2n plus n squared over 2 plus n over 2. Oh, and we are going to have to account for the retrieval from the array as well. Yeah, the array access. Thank you. I'd forgotten about that. Excellent point, Sean. So this would actually be, we would also need, a memory lookup from the array, and we'll need n of those as well, right? So that's a very good point, right? Because we'll have to look up 1 coefficient for each loop from our array. So we'll need n memory accesses, right? So maybe I should make this a 3n. Assuming that our array retrieval is O of 1, yeah, which I think that's a fair assumption. I think that would be constant time, right? So in terms of big O notation, this algorithm is going to be big O of what? What do we do when we find the big O of this expression here? N squared, right? Because all that we do is we take the largest power and ignore all the smaller powers and coefficients, right? So this would be big O of N squared. Okay. So let me ask you this. If our multiplication is giving us an N squared algorithm, the rest are linear, right? All of these guys are N. So everything else is linear, but our multiplication is squared, right? So that's right, Sean. Calculating the power is the costliest part. That's exactly right. So what I would like to do is see if I can come up with a different way of coding this thing so that I can come out with, in total for my big O notation, come out with just a linear function, right? And that's according to something called Horner's rule. So this guy Horner came up with, this faster way of doing it, right? So what do you guys think? Is there an easier way to do that? Okay, you linearize the power by storing x power I out of the loop and multiplying it by x each time that we loop. Okay, so let's try another function here. Here's f2. It's going to take the same arguments, double our array, which has n items in it called the c for the coefficients, and double x. Okay, so we want to have another variable other than the sum. So I'll have sum equals 0 and x pow I is what you want to call it. That's fine. Equals, what do we want to initialize this to? 1. Very good. Okay. Right, and then we'll have our for loop again. Same for loop. Int I equals 0. I is, oh, and this should have been less than or equal to n. I forgot to correct that last time because we have to include that n value for our largest term, right? But that's okay, that's fine. So I have I less than or equal to n, I plus plus. And now what are we going to do inside of here? Add to sum first. Okay, so we have sum plus equals what? Okay, the array at index I times x pow I. Make that a little cleaner there. Okay, x pow I, good. And then what's the second part? Yeah, very good. Then we have x pow I times equals x. And finally, we'll return the sum, right? Okay, we get both functions on there at once. Okay, good. So now let's rehash this situation, right? So we'll have memory accesses, comparisons, additions, and multiplications. Those will be our 4 operations that are not constant. We also have some constant operations. We initialize this variable once. We initialize this variable once. We initialize this variable once, right? Ooh, and we forgot our additions. We're also adding on to I in here, right? So we also have inits. We have 3 of those, right? And actually our additions, we're adding on to I and adding on to sum. Sure, and you can switch around the additions of I, but we're not going to get quite that detailed, right? So let's go through it one more time. So our memory accesses, how many operations of that are we going to need? That's right, Sean. It wouldn't change the big O anyway. That's true. Yeah. So how many memory accesses do we need? How many times? Yeah, n plus 1, sure. And it actually should have been n plus 1 before as well. These should all be plus 1, right? And this actually n should have been 2n plus 1, like that, right? That's a little better. Okay, how many comparisons? None of this changed the big O, right? It's still big O of n squared, even with these little changes that we made. It's still the same thing, right? N comparisons, or n plus 1 if you want, depending on how accurate you care to be. Okay, the number of additions. Yep, 2n, or 2 times n plus 1. Okay, and multiplications. Two n, yep, because we've got to multiply here and here, right? So again, 2 times n plus 1. Now, the reason why I didn't care about these plus 1s before, I didn't even bother to think about it, is because I've been doing this a long time, right? Is because it won't affect the big O notation at the end of the day, right? All that stuff gets thrown in the trash anyway. So if you want to do an accurate count, that's fine. But if you're only going to just throw away all that accurate count at the end when you go to your big O notation, then why bother doing it in the first place, right? But either way is fine, right? Doesn't matter. So we've got how many n's here? 1, 2, 3, 4, 5, 6. Right, so we've got 6n plus 1, 2, 4, 6, 9, which again, this coefficient doesn't matter. This additional constant doesn't matter. For our big O notation, it's just big O of n, right? Which is why I didn't really bother to think about those. Yeah. And so you can see using Horner's rule, where we keep track of our multiplies of x as we're going, we can save a bunch of operations and save a bunch of multiplies. And this algorithm will be linear, whereas this one is quadratic, and that's going to save us lots of time, right? What do you guys think? People happy with that analysis? Questions? While you think about it, I'm going to get some more water. I'll be right back. All right. So Lucas, you're wondering if compilers can see this optimization. You mean, would a compiler be smart enough to change your function to be the linear one instead of the quadratic one? Is that your question? Yeah. I don't know the answer to that. I was a math major in undergrad, not a CS major, and so I did not take a class on compilers. And so I just don't know. If it was smart, it would figure it out, but I'm not sure how smart compilers are. I would hope that it would see that, right? If you keep, modifying the same variable and reusing it over and over, then you would hope that whoever made your compiler would say, oh, well, we can get a nice speed up by just using another variable instead. But that's not my area of expertise. Yeah, I'm just not sure. Yeah, I would hope so, but I don't know. Yeah, it's a great question. Really good question. Yeah. Yeah. Okay, other questions? That's right. Yeah. From math, you can do computer science, but computer science can't go to math. Yeah, there's this hierarchy of majors that you can go down, right? Yeah, you can go from physics to math, but not math to physics, right? You can go math to CS, but not CS to math. And then from there, right, you sort of go down the list, right? Down to biology and psychology and anthropology is right down there at the bottom, right? There was a running joke at my college about the hierarchy of majors, and everyone would poke fun at each other. All right. Well, I don't know. Not at my school anyway. It depends on the school as well. It varies, right? Okay, so so that concludes our discussion of Big O notation. Right? Does anyone have any other questions on Big O notation generally? Stuff on the proofs, Weber questions. Oh, I do have your midterms graded up, so you can check your grades on those. Any other questions before we jump into chapter 12? Okay, cool. So we're going to begin our discussion of the theory of computation with languages and regular expressions. Okay, so we're going to start out by talking about languages. Okay, and this is going to be annoying because we're going to use some of the same symbols over again, and now they're going to have totally different meanings. Okay, so here goes. So in a language, you have an alphabet, which is called sigma. Not for some, now it's the language, right? And sigma is a finite set of characters. Okay. Then you can have a string over the alphabet sigma, which is a finite sequence of characters from sigma. Or the empty string. And the empty string looks like the element of symbol, but it's just bigger, right? So this means the empty string, which is the string with no characters in it, right? Now your book does it this way, right? But I like to do it the script way to differentiate it from the element symbol because it looks too similar to me, which is annoying. So I like to do it this way, right? A curly E. So the pointy E is sigma. That's the, the alphabet. And the curly E is the empty string, or the, not curly, but curvy is what I mean. Okay. So we also have the length of a string. The length of a string. And what do you think that is? Number of characters, right? The number of characters in it. I mean, in the sequence, right? Okay. And finally, we have the language. Language, which is usually denoted L over sigma, is a set of strings. Using the alphabet sigma. Okay. And I think this shouldn't really be news to you, right? Because English works this way, right? English has an alphabet, A through Z, a finite set of characters, right? You can have strings in our alphabet. What are those called in English? Words, right? So strings are just like words, basically. Okay, you can have the length of a word. So what's the length of the word cat? Three, right? 3 letters in the word cat. Okay, it's pretty straightforward. And the language is a set of strings using the alphabet. Okay, so the English language is a set of words, right, that use those letters A through Z, right? Some strings are in the language, right, like cat, and other strings are not in the language. So can someone give me an example of a string over the alphabet A through Z that is not a member of the language set of English? Good. XZWB. That is not in the English language, right? So some strings are in the language, some are not. Is everyone good so far? Any questions? The formal definition does not include any rules about syntax. Nope, none. It's just one rule. It just has to use the symbols from the alphabet. That's it. Yeah, that would be a grammar. Yep, that's right. And we're actually going to talk about grammars, but that's coming up. Right, different kind of thing. Okay, so there's a few different languages that have specific names that we're going to talk about. Okay, so sigma to the n is the language. Let me do a little line here. So now we're talking about specific languages. Is the language of all strings over our alphabet sigma with length n. Okay, so let's do an example, right? So let's say that that I want to know, now the language is a set, right? It's a set of strings. So what would be the size? So let me define my alphabet first. So if my alphabet is the set A through Z, right? So all 26 letters, right? Then what's the size of sigma 3? The language of all strings of length 3 built of 26 letters. Good, right? 26 cubed, which is P26.3. Yep, exactly. The number of permutations of 26 letters, pick 3 of them, be 26 cubed, right? So you'd have AAA, AAB, AAC, all the way up to ZZZ, right? Question so far? Is everyone good there? Okay. Here's another definition for you. Sigma plus is the language of all strings over sigma with length greater than or equal to 1. Okay, so that little plus means, like positive, like the positive real numbers, but now we have the positive language, right? Which is to say, it's the all the strings that have a positive length, right? Length greater than or equal to 1. Okay. Whereas sigma star is the language of all strings over sigma. End of story. Can you have a string of negative length? No, but you can have a string of 0 length. So in other words, the empty string is not an element of sigma plus. See why I like the curly E instead of the element E? Because otherwise this would look really gross, right? So all that it's doing is it's eliminating the empty string. Does that make sense, David? Yep, cool. So let me ask you this. With our previous alphabet, sigma equals A through Z, what is sigma star, or sorry, what is the size of sigma star for the English alphabet A through Z? Yeah, infinite. Which infinity is it going to be? Is it the natural numbers infinity? Is it like the 2 to the infinity kind, the bigger one? Any thoughts there? Aleph. Be more specific, Shangs. I'm not sure if you're saying what you actually mean. Do you mean the smallest infinity or one of the bigger ones? The lowest one. Yeah, that's right. So the lowest one's actually called Aleph naught. So it's here. I should write it. It's oh boy, but I have to write an Aleph that way. Let's see. I always forget how to do it. For being a visually minded person, I really should just take the time to learn how to draw it correctly. I'm going to look it up. I'm going to learn it once and for all right now. That's annoying. Here, you can learn it with me. It's going to be great. Should know how to draw an Aleph. So there's an Aleph, right? So you got a diagonal, one of these, and one of these, right? So Aleph naught is the regular infinity, right? And Aleph 1 is the next higher one, which is 2 to the infinity. That's Aleph 1. Okay, so it's a diagonal, a squiggle, and then a little sideways T on it. Okay, so that's an Aleph. Mine's not as pretty as the script on the font online, but that's okay. Okay, and you're right. It is the smallest infinity. That's true, because think about how many strings you can make. Well, how many strings of length 0 are there? 1, right? How many strings of length 1 are there? 26. How many strings of length 2? 26 squared, 26 cubed. And you can have the strings be as long as you want. So the size of the language, and here's where this is going to get real gross, right? The size of the language star, sigma star, is going to be equal to the sum, which now this is the other sigma, right? From I equals 0 to infinity, right? And that's going to be our string length of, and how do I want to do this? Of 26 to the I, right? Which of course is equal to infinity. Is everyone happy with that? Bless me. Yeah, the infinity of real numbers is Aleph 1. Yeah, that's correct. Mm-hmm. Okay, so no questions there? Happy. Okay, cool. So moving right along. Now let's talk about ways to combine languages. So let's say we have two languages. Over sigma, some alphabet called L and L prime. So two different languages. Okay. The concatenation is denoted LL prime. So you just put one language after the other, right? It's kind of like multiplication a little bit. It's just implied. You just put the things next to each other and multiplication is implied. With languages, you put the languages together and concatenation is implied. And that is the set of strings x, y, such that x is an element of L and y is an element of L prime. Okay. The union is denoted in the usual way. So that would be L union L prime. And that's what you think it is. You take the strings from both languages and put them together. So it's the set of strings such that x is an element of the first language or x is an element of the second language. So basically you just put the two languages together, right? Here, concatenation, you glue one string after another. Here you get to pick from either language. And finally, the Kleene closure is denoted L star, and that is the set of all strings x such that x is a finite concatenation, or let me do it this way, concatenation of finite strings from L. Concatenation of a finite number of strings that are an element of L. Concatenation is not commutative. Yeah, so we're going to do some examples, right? So, so let's just concatenate two strings, first of all. This is a string concatenation. This is a language concatenation. So let's just say we have two strings, right? So if I have string 1, let me just call it S1 equals ABC, and S2 equals DEF, then what would be S1, S2? Let me make these string literals in the usual C++ denotation there. So it would be the concatenation of those two strings. A, B, C, D, E, F. Perfect. And you even got the double quotes. Excellent. Okay, so it's not commutative because the other way would be D, E, F, A, B, C, which is not the same. That would be called S2, S1. So not commutative. Great question. Okay, so let's talk about the concatenation of two languages then. So in that case, we're going to have, let's make two different languages, right? So we'll say L equals the set, A, B, C, and D, E, F, and L prime is the set G, H, I, and J, K, L. So what would be the concatenation LL prime? So how about just the first one? We'll just go one at a time. All right, so what would the first string in that concatenated language be? Okay, A, B, C, G, H, I. Excellent. Okay, next one. I'm sorry. I missed the first thing you said, David. A, B, C, D, E, F would not be in there because you have to have the first part come from the first language and the second part come from the second language. So A, B, C, D, E, F doesn't count. Does that make sense? No, so these are just strings, whereas these are languages. So here, two different examples. Sorry, I was being confusing. Oh, that was, okay, I see. That was your last answer. Okay, sorry, my bad. I just read it wrong. Okay, so what would the second string be in the concatenated language? I'm glad I misinterpreted it because it was a good wrong answer, right? An illustrative incorrect answer. A, B, C, J, K, L. Perfect. Okay. So this is a lot like the cross product, right? You take the first two, these ones, or foiling is another way of looking at it, right? First, outside, inside, last, right? So the next one will be A, B, C, J, K, L. What about the third one? D, E, F, G, H, I. So that's the inside. Good. And finally, the last one, D, E, F, J, K, L. Very nice. Okay. And the union of these languages? Good, right? So A, B, C, D, E, F, G, H, I, J, K, L, right? A, B, C, D, E, F, G, H, I, J, K, L. Yeah, J, K, L. Yeah, instead of O. Yeah, it's just a typo. Okay, cool. Let me ask you this. What would be the size of the Kleene closure of L? Any concatenation of a finite number of strings from the language. Power set I'm not sure what you're getting at there. Power set I empty set. Power set minus the empty set. Not exactly. Well, the power set of what? Do you mean like the power set of L? Of the subset of L that the Kleene composure is composed of. Sorry, Kleene closure is composed of. I said composure, I meant closure. Sorry. Not exactly, because the power set in this case, the size of that power set would just be 4, right? Because there's 2 things in here, right? But this could be any finite concatenation of strings. So let me do this. Let's list out some elements of the Kleene closure of our language, right? A, B, C, D, E, F. So first of all, here, I'll do it this way. So first of all, the empty string actually is in there because no concatenations is a finite number of them. Yeah, you can do it multiple times, exactly. And you can do it no times, right? So the empty string is in there, as is ABC and DEF and ABC and DEF, def, right? And of course, ABCDEF is in there, and so on. So the size of that is going to be how much? You have to have a finite number of concatenations, but is the set itself going to be infinite? So you can have 0 copies or 1 copy, 2 copies, 3 copies, right? As many copies as you want. Right? Yeah, so it would be infinite. That's right. The size would be infinite because you can have any finite number, which means you can have 1 of them or 2 of them or 3 of them or however many, and all the different combinations of those, right? So it actually would be an infinitely sized set. Cool. Okay. So okay, one more set of definitions, and then I think we're done here. And we can do some examples. Okay, cool. This is fun, I promise. We're almost done with the gross part. The definitions are always rough, but once we get through those and do some practice problems, you'll get to enjoy this, I think. Actually, in the next section, the practice problems in this sections are kind of rough. The next section is where it gets interesting. But one word definition first: a regular expression. This is what we're leading up to here. Over sigma, right? So first of all, the empty set and the empty string and the elements, let me call them, because we're calling them characters, right? So let me call them characters that are elements of sigma, are regular expressions. And so I'll just use C to mean individual characters inside of the alphabet, right? Secondly, if R, let me do it this way, R and S are regular expressions, then 3 things. The concatenation RS is a regex. Secondly, R or S is a regex. And thirdly, R star is a regex. And some examples are going to be really helpful here, right? I realize this is very abstract, right? So we'll do some examples. Okay. So let's have, as an example, let's have sigma be the alphabet ABC. Okay. So here's a regular expression for over sigma, right? Let's list out a few of them, okay? So first of all, the empty string and A and B and C are regexes. Regular expressions. I'm just abbreviating regular expressions. Okay. So is a concatenation of any two regular expressions we have already. Well, here's what we're starting with. Here's our regular expressions we're starting with. We can concatenate those, right? This is operating recursively. These are like the base cases, and these are the recursive cases. So we have multiple base cases, multiple recursive cases, right? Or inductive cases, if you want to think of it that way. So using the first rule of concatenation, someone give me a regular expression that uses these base cases. Any ideas? AB, right? Good. What else? Good question, David. The difference between in the empty set and the empty string is that the empty set just doesn't have any strings in it, right? And the empty string is actually a string, right? But it's a string with no letters. Okay, so Lucas, you got a bunch more of the twofers, right? So we got AC, AB, oh, we did AB, BA, we got AA in here, right? We could do BA. You could also take these ones that we've been doing and use these and then recurse again or do another inductive step. If BA is a regular expression, so is BAC, right? Or CCABA. You can make these as long as you want, right? Because you can continue to apply this rule recursively to make your strings longer and longer inside of your regular expression, right? You could also use this, what's called the OR symbol. And this is called the star or the Kleene star, right? So this is concat. I should label these guys. So here we just use the concatenation rule. Here we just use base cases. So let's try an OR, right? So if we have, and these regular expressions, I suppose I should have said, these are languages, okay? The regular expression generates a language, okay? So if we just had a base case, right, then that would just have one thing in the language. Like if we just had B, okay, well then our language is B. Same thing for concatenation, right? If we just had BA, okay, then our language is just BA. But what if I did something a little bit more interesting? What if I said, A or C? Well, the language that corresponds to that is the language A and C. What if I said, A, B, or CB? Well, that's going to give us the language AB as one string, CB is the other string. Okay. What if I had the language A concatenated with B or C? What language would that give us? Any guesses? Good, A, B, and AC, right? Because we have A concatenated with B, or A concatenated with C. So A, B, and AC. And this can start to get interesting, right? What if I had, you know, A or B, A or B or C? I concatenated those three. So first of all, how many items are going to be in my language here? 6. Very good. Can you list them? I'm going to stop putting the double quotes around it because it's getting tiring. All right, AAA, AAB, AAC, right? I do this A, I pick the A from here and pick any of these three that I want. Or I could pick the A from here, the B from the second one, and then any of these three that I want. ABA, ABB, ABC. So that's exactly right. You see how the concatenation and the pipe work together? Questions? Yeah, makes for an interesting combinatorics problem, right? Because you have 1 choose 1 times 2 choose 1 times 3 choose 1, right? Which just turns out to be 1 times 2 times 3. And the combinatorics are going to get more interesting as we go, right? Okay. Let's incorporate the star, right? So remember, the star of a language is any number of repetitions of the contents of the language, right? Of the words in the language, or the strings, and strings are when words are the same thing, right? So any number of repetitions of any of the strings in the language, okay? Well, here we're building up this language where we have, you know, A, B, and C are these regular expressions. Well, you know, these start out to be whatever symbols you want, and then you can do multiples of them, right? So let's do, let's see, what should I do here? Let's do A star, B or C. Now this language that gets generated is going to be an infinite language. Okay, so we're just going to do some of them, right? We'll just do the first few. So let's go in order from shortest to longest. Well, not longest because it's infinite, but let's start with the shortest strings that are members of that language. So remember, star could be any number of A's, right? So what's the smallest number of A's you could have? Zero. Okay. So then what would be an example of one of the shortest strings in this language? B. Excellent. And what's the other one? C. Now let's do the length 2 strings. So what would those be? A, B, and AC. Okay. What about the length 3 strings? AAB, AAC. I see you made the typo, but that's okay. AAB, AAC. Right? So it's any number of A's followed by a B or a C. Right? So that's combining all three symbols. Star, concatenation is implied here, and then the or. Right? Okay, so let's do another example. What if I say A or B or C star B? So now what's going to happen? Can someone just give me an example of one string in this language? Any length you want, doesn't matter. Okay, so let me say it one more time. It seems like you guys are stuck. You can have A or B or C, and that you can do as many times as you want, followed by B. Okay, so you could have an A with a lot of B's afterwards. That's not quite right, because the star is applying to the first thing, not the second thing. If I had A or B or C and then B star, then that string, David, would work. But in this case, it's not quite right. You got another idea for me? Kind of the opposite of what you said, in a sense. Actually, I'm sorry, David. No, your string does work. It's just complicated. But no, your string does actually work. But let me circle back to that after a couple of examples first, because your example's complicated. If it's just B's, it absolutely works. But let's start with this one. A, B. Okay. Any number of A's you want, right? Do you want an A? Okay, and then you get another one, another A, and then you get another one, another A, then another one, another A. Finally, you say, okay, I've had enough of A's. I'll put a B at the end, right? If it's all B's, you could do the same thing. B, 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 B. That works, right? So I could take a B, do something else, a B, do something else, a B, do something else, and then here's my last B at the end, right? I could also do, A, B, C, A, B. That's fine, right? Because as many times as you want, you can pick an A or B or a C, right? So first I pick an A, then I pick a B, then I pick a C, then I pick an A, and then I have my B at the end. Yep, so David, that example works. And so does your original example of just A with a bunch of B's after it, right? So if I have A, B, 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 just a lot of them, let's put that many, so I'm getting bored. Well, first I pick an A, right? Then I pick a B, and another B, another B, another B, till I get to the last one, and the last one is this final B at the end, right? What do you guys think? You've already answered the next question I was going to ask, David. You're getting it, right? An English description of this language is the set of strings over the letters A, B, and C that end with a B, right? Any string that you want, as long as it ends in a B, is what this language here describes, right? So you can actually have little English descriptions of these formulas, right? Awesome. Okay. Let's, I think that's all I want to do for that. Yeah, let's try a couple more examples here, right? So let's do a different language. Let's switch over to a binary. So my alphabet here, scroll that down here. My alphabet is going to be the numbers 0 and 1. Okay, so I'll switch from letters over to numbers, but they're still just symbols, right? And so what if I have the language 0 star, 1 star, or 1 star, 0 star? Okay, let's do a few examples of strings in this language. Empty string, good, I agree. Not any binary string, that's not quite right. There are some strings that are not going to work. For example, 101. 101 would not be in this language. But let's hold off on the ones that aren't in there for a minute. Let's do the ones that are in there. And then we'll do the ones that aren't in there. And then we'll see if we can come up with an English description for what this language is. Right? So 3 steps. Right? So first of all, let's have some that are in the language. Okay, 11100. Okay, 11100. And which part of this, the or did you use? Did you generate that string using the first part or using the second part? Yeah, the second part. Yeah, absolutely, right? Because you have some number of ones followed by some number of zeros, which is what we've got here. Okay, so let's try to generate a string using the first part of the language. Hey, Sean, you're on it. 00011, right? How about the string 11111? Would that be generated by the first part or the second part? Good, trick question, either one. You guys are getting it. Awesome. Yeah, very good. Okay, so, and there's lots of different strings that we could have in here. Okay, how about some strings that are not in the language? So I'll say not in it, not in L. Okay, 101, like I told you, because there's no way to find that. I would have to go for the second part because I'm starting with a 1, right? Since I'm starting with a 1, it has to be this one, right? And then I have a 0, okay. But then I have another 1 on here, and there's no way to generate that from my regular expression. There's no way to get that extra 1. So 010 is also not in there. Excellent. Let's have one more. Zero, 1110. Great. Very nice. Right. If we wanted to do one more, right? That one's not in there. That switches back and forth between 0 and 1 4 times. 0, 1, 0, 1, 0, 1, 0, 1, right? And here you're only allowed to switch over once, right? So with that little hint, how could you describe this language in English? Or I should say the language generated by this regular expression. That's the proper terminology. So could you describe for me in English the language generated by this regular expression? Good, perfect, Lucas. Any number of ones followed by any number of zeros, or any number of zeros followed by any number of ones. Very nice. Okay. How about this language? 0, 0, or 1. I'll start putting serifs on my ones. That'll help distinguish it from the pipe. Right? Should have done that from the beginning, but that's okay. I realized it now. Okay, let's do a few examples here. What's the shortest string in this language? 0, okay. Let's do 2 more examples of strings in the language. 0, 1, 0, 0, sure, 0, 0, 0, 1. We could also have a longer one. We could have 0, 1, 1, 0, 1. Right, that's in there, etc. In English, how would you describe this language? Any string that starts with 0. Very nice. Yeah, great. Okay. So All right. Now we're going to do something a little harder. This is where it gets fun. Now we're going to start with an English description of a language, and we're going to write the regular expression that generates it. Okay? So let's start with a language consisting of zeros and ones that have even length, and the zeros and ones alternate. So even length with alternating zeros and ones. Let's just do some examples first, right? So what are some examples of strings in this language? One zero. Okay, that's one of them. Excellent. Even length, and the ones and zeros alternate. Let's have a few more. Zero, one, zero, one. Okay, great. I'll give you a freebie. The empty string is in there because that has length 0, and 0 is an even number, so that counts. Let's do one more. One zero, one zero, one zero. Excellent. Great examples. And now let me ask you, what's the regular expression that generates this language? Very nice, Sean. 0, 1 star or 1, 0 star. You can either have as many alternating pairs of 0, 1 as you want, or you can have as many alternating pairs of 1, 0 as you want. Great work. Nice. Okay, let's try another one. Strings of zeros and ones with an even number of ones. Even number, I'll say even total number of ones. So let's do some examples. So what's an example of a string with an even number of ones inside? Okay, 1, 1, 0. That's a good one. It has 2 ones inside, so we're good. Okay, let's have a few more. Okay, 1, 1, 1, 1. Great, that has 4 ones inside, so we're golden. The empty string, that has no ones inside, we're good there. 101, very nice. Right, we could have the zeros interspersed inside the ones. We still have 2 ones in the string, still have an even number of ones in the string. So we're good on that. Good one, Haruka. Let's have a few more. Maybe 2 more. Okay, 1, 1, 0, 0, 1, 1. Great. One more. Okay, 2 more. Okay, great. 1, 0, 1, 0. Great. 0, 0, 0, 0, 0, 0. Awesome. Okay, so there's a bunch of good examples there. And now for the hard part. Let's try to build a regular expression that generates these strings. right? So first of all, I want to think about how to get an even number of ones. Okay, so all right, so we got a few different ideas. Okay, so David, let's start with your idea. If you have 0 or 1 1 star, that generates most of them, but not all of them. So can someone think of a string that should be in our language, but is not in David's language? And David, you got it. This is the 101. Very nice. Okay, so Sean, let's think about your idea. So now we have 101, 011, 11, or 110 star, right? So that has the zeros interspersed, but that doesn't capture everything either. Misses the 0 by itself. Yep, good. Okay, so Sean, yours misses the single 0, which should be in the language. Okay, let's look at Lucas's. You have 1 and then as many zeros as you want and then another 1, or 1 1 or 0 star. Okay, so I think that might work actually. Can anyone think of a string that's not captured by Lucas's language? Or an equally important question, does Lucas's language give us a string that shouldn't be in the language, right? So you got to ask two questions. Does it capture everything? Does it miss everything? Or does it do too much, right? And either way is wrong, right? So if you miss some things, like our first couple ideas from Sean and David, right? That's bad. But also if you include extra strings that are not supposed to be in there, that's bad too. I'm not saying Lucas's language does that, but you do have to think about both sides of the coin, right? So what do you guys think? You think Lucas's language is good, or does it miss something, or does it do something that shouldn't be in there? Any ideas? You think it looks good? Can anyone think of a string that it captures that shouldn't be there, or a string that should be there that it doesn't capture? Looks good. Okay. I think it looks good too. So here's what we've got. We've got 101, 10 star 1, or 11, or 0 quantity star. Okay. And that is right. But there's a shorter way of writing it. Anyone see which part of it, how we could simplify this a little bit? Make our regular expression a little bit shorter that still captures the same language? This is a common problem because people often forget that the star means that you don't have to have any of that thing. You could have no zeros or 1 0 or 2 zeros. Yep, this thing is not needed, right? You don't need to have 1 1 because that's already captured by this first chunk. All you have to do is not have any zeros inside. So this is actually the same as 1 0 star 1 or 0 star. Oh, sorry, or 0 quantity star, pardon me. Do it this way. There we go. It's a little better. What do you guys think? Make sense? I'm painfully aware that we went from some really boring and intricate definitions to some really simple examples, followed by a really complicated interweaving of brand new symbols you've never seen before. I get that, right? This is not easy, okay? But hopefully you can see that it's fun, right? It's like a little puzzle, right? Let's try one more. Okay. Strings that don't have consecutive ones. Okay, so let's do some examples. Okay. 0101. Yep. Just a regular old 01. Yep. Let's have a couple more. Empty string. Yep. Two more. Okay, 1001. Awesome. One more. Okay, 0100. Beautiful. Now this is going to be interesting, right? So what do you guys think? How can we make a regular expression that will capture this language? Okay, 100 star quantity star. Very close. Very, very close. And I don't actually need to put the parentheses in. The concatenation is just implied, right? So Sean, you can put the parentheses around the 0 star, but you don't have to. And then this whole thing is star, right? Okay, that misses the 0 by itself, right? The smallest string you could have in here is 10, right? I think we're also missing 01, right? So we want a 0 star out front. Does that fix it? Now we're still missing the, okay, so now we've got 0 by itself, but now we're missing 01. Yeah, we're missing 01. Okay, so Lucas, you have a very different answer there. Okay, so before we get into Lucas's, can someone see of a way to fix this so that it will include 01? So Lucas, you're saying it's pretty much the same. Okay, so you have that 0 star 0. Okay, I see what you're saying. So you have those extra parentheses in there. That's what threw me. And you said, Lucas, you're just saying, or you can have an extra 1 at the end. Ah, you just want to put 0 or 1 at the end. I think, Sean, that's a nice way of doing it. I think, Sean, that's a nice simplification of Lucas's answer, right? We can just put 0 or 1 at the end. Does that do it? Oh, and Luan, sorry, I missed yours. Luan, since you have that 0 or 1 star at the end of yours, that's going to allow multiple ones in a row, which is not allowed. Does that make sense, Luan? Okay, yeah, you see it. Okay. And Lucas, you're saying now 10 is no, yep, now we don't have 10 anymore. Uh-oh, because now we have the 10 from here, but we have to pop another 0 or 1 after it. Okay. So I think this one might have gotten too gross, right? Because we started off with a good idea, and then we just kept adding junk, right? And that works sometimes, but you have to be careful because if you just keep adding junk, sometimes you can get yourself down a path where you paint yourself into a corner, right? And I'm not sure if we've done that here or not, but once it starts to get this long, oftentimes it's a good strategy to sort of think about it and start over, right? So let's try that, right? And the whole thing can be empty, right? Yeah, so this 0 or 1 contradicts. We can't put a star on here because then we could get multiple 1s in a row. So that doesn't work. right? Zero or one or empty at the end. Ah, okay. Zero or one or empty. Does that fix it? Let me do this. Let me tell you what the book has, and let's see if we can see if they're the same or not, right? So here's what the book says. See if this is equal to the book's answer, which is 0 or 1 0 star followed by empty or 1. Make these a little bit straighter and longer. Okay. So what do you guys think? Are these the same? I mean, it's sort of the same idea, right? Because you have this, does it have 0 1 0 1? I think it does, because we would have 0 and then 1 0 and then a 1 at the end, right? So you'd break it up into 3 parts: 0 1 0 1. Yeah, nice. Good question. That was a tricky one. Yeah, I think they're the same too. I think either one of these two ways will work. I think you did capture it by putting that or empty at the end. I think that's got it, right? Um, and the way to think about this, here's the way to think about the book's answer, is you have a string of zeros or 1 zeros. So you can't make consecutive ones, because anytime you put in a 1, you've got to put a 0 after it, right? Or you could not put in a 1. That's okay. You could put as many zeros as you want. But if you do put in a 1, you got to put a 0 after it to avoid those consecutive ones, right? So you can put a 0 or a 1 0, as many as you want. And then your string may or may not end in a 1, right? Which is okay, because you have that padding 0 right here in case you had a 1 right before the end. If you had a 1 right before the end, there has to be a 0 between that and then the final character. Does that make sense? Questions? Okay, cool. So we're about halfway through. So let's take a break. Then we'll come back and do some practice problems. We'll do a bunch more practice problems like this. Try to get you guys as comfortable as we can be with these regular expressions. So get up, get out of your chair, take a little walk, get some tea, whatever you gotta do. We'll come back in 10, do some more practice problems. See you soon. All right, so we'll do some practice problems here, another little bit of exercises, and then we'll jump into our next totally new mathematical structure that we're going to learn about. So let's start with the numbers 16 through 18. Let's write 5 strings that belong to the language defined by the given regular expression. So we've got 0 star 1, 0 star 1 star star. So what do you guys think? Let's just do 3 strings. That's enough. Just get you guys a little practice. Well, Lucas has got 4 already. Okay, so we can do a single 1, okay, a 0 1, yep, because the star means we don't need to. Oh, and then we just put you. So you are lazy, Lucas. I see what you did. So you're only doing the 0 star, as many zeros as you want, followed by a 1, and you didn't use the second part. Okay, so let's do another string where you use that second part over here. Of course, you don't have to use it because of that star on it, right? But let's do one where you do use it. Okay, 1 00011, right? And you could actually have multiple sets of 0 1s afterwards because of this star. So you could even have, 010101, and that would be buildable as well, like this, right? So you could have 1 0, the first 0 1 from here, the next 0 1 from there, and the third 0 1 from there as well. Okay, so let's try 17. B star or B star A B star. So what do you guys think there? Bab, that's a good one. Okay, just a single B, great. What else? Just an A by itself, sure. What else? I guess you did 3 of them. Good enough, right? Could also have B, 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 A, right? The empty string, definitely. You could also have a bunch of B's and then an A, or an A and then a bunch of B's, right? You could generate those with this second part over here, right? Could you describe in English number 17? What set of strings are those? So I realize on the next part that's what we were going to do, but how would you describe in English number 17? Yep, strings that have at most one A. Perfect, that's exactly right. Okay, let's try number 18. What do we have here? We'll just do some examples, right? So what do you guys think? Okay, we got an X, Y, X, X, Y, X. Yep, that'll work. Okay, let's have a couple more. Okay, we have 3 copies of YXXY. Perfect, that'll do. Okay, and one more. All X's. Yep, that'll work as well, because we just take the X here and star it, or we could even do the X in the front and star it. Either way, or a combination of both. We could do, the first 4 X's from here, the second 4 X's from that one, however you want to do it. Great. Okay, so let's try 19 through 21. So we'll start with 19. How would you describe in English what this string is doing, or what this, what this regular expression is doing? So you have B stars interspersed between A's. Okay, so you have 3 A's with any number of B's in front of each of them. Okay, cool. So that's one way of putting it. That's great. Let me put it a little bit differently. A string with 3 A's that ends with an A. How about that? What if we wanted to have only just the string, the set of strings with 3 A's? How would I modify this so that it's only the string, so it's any string with 3 A's inside. What would that look like? Yep, just put a B star at the end, right? Put a B star right there, and that'll be all the strings with 3 A's inside. Nice. Okay, how about 20? How would you describe that one? Okay, any strings that starts with a 1, anything you want, and ends in a 0, 0. Perfect, nice work. Okay, and number 21? Any string where the second character is a Y. Great. What if I put a star on the first clause? So I had, X or Y star, Y, X or Y star, like this. How would you describe that one? Any string with at least one Y. Perfect. Yeah, very nice. Okay, so I think you guys are getting it. Let's move on. Okay, so we got 22 here. We're just supposed to say if these strings are in the language generated by that regex or not. So this first string, AAABA, can you generate that from this regular expression? Yes, good. How does it work? So here, what do you pick on the first, I'll just call it a clause, right? Empty, okay? And then you have an A. What do you get from the third clause? AA, close. Not, yeah, AAB. So you have A, and then you need AAB, and you have your final letter, the A, and then empty. Yep, very nice. Okay, cool. We got there. Any questions on that? Did that make sense? So you have A, AAB, A, empty, right? Okay, what about this one? BAABB. Or feel free to jump in with questions if you've got them. But if not, let's jump into that. BAABA. That's a no. Okay, why not? You have to have an A at the end or just one B. You're missing one A. Ah, okay. So here you have, right? So here you have 2 A's and then 2 B's at the end, right? So to get there, you would have to have a B. Okay, so let's go through it. So you'd have a B at the front, right? You couldn't start with the A, right? Because you're starting this one with a B, right? So you couldn't have an empty here. You have to have the B here to start it off, which means this A has to be this one. Then here, okay, then you can generate an A, but that A has to be this one. Let me get a better pointer. There we go. My finger's too fat. Okay. This A has to be this one because you can't do A, B, right? So you have to, okay, let's start at the beginning. Okay, so you have your B, you have your A. This A has to be this one and not generated from here, because if you generate your A from here, then the B has to be generated from here, because you can't have this A generating it. And if the B comes from here, right? Then this b has to come from here. And then there's no a at the end to account for this. So that doesn't work. So you'd have to have b, a. The third a has to be that one. But then your b is going to come from here, and you've run out of letters, and this b is unaccounted for. Right? What do you guys think? It's good? Kind of complicated. It's quite a sneaky little chain of logic there. Questions? Are people lost? What do you think about that second one? Does that make sense? Yeah. Okay, Luan's got it. Makes sense. Makes sense. Okay, great. Okay, so let's try the next one. And again, feel free to jump in with questions if you're lost. Happy to go through it again. So we've got z, y, y, x, z. Is this one generated by the regex? No. Okay, why not? Can't have y, y. Well, I think you could have a y, y, right? Can't you have this y without any x's and then this y again without any x's? Oh, there's no way you get an xz. Okay, that one I do agree with, right? You can't have an x and then a z because you'd have to have your x's coming from here and then a y, which would come between the x and the z, right? So Sean, I think you've got that one. Okay, how about zizzy? Z, Y, Y, Z, Y. Can we do that one? That one's fine. Okay, so how do we generate that one? Which clause do you use? Yep, Z, Y, Y. So you're using the second clause twice, it looks like, right? So you have Z, Y, Y, and then do it again from this star, and then Z, Y for the last little bit over here. Very nice. Okay. And let's stop there. I think that's enough practice. I'll leave it for you guys to work on 25 through 27 if you need a bit more practice, well, let's just do one more. I'll leave 26 and 27 for you. But let's do 25. The language of all strings of zeros and ones with an odd number of ones. Right, so that we'll make that our last one. So here, let me switch back over to my paper here. Oh boy. So many things moving around. All right. So we have sigma is 0, 1. And we want an odd number of ones. Okay. And we want, of course, a regular expression that will generate this for us. So what do you guys think? Okay, so let's do. So you got some examples there, Luan. That's good. Let's start out with examples. So we've got 1. We've got 0, 1, 0. What else have we got here? Okay, we've got 0, 1, 0, 0, 101. I think that's a really nice example. That's a pretty one, right? I think that that's going to be really helpful for generating a regular expression. You guys see how, oh boy. You guys see how this might work? How to do the regular expression? Or can you sort of just describe in English? Okay, so that's going to be part of it, right? Starting off, we have a single 1, okay? So we have 0 star, 1, 0 star. Okay, so we have a single 1. So these are all the strings that have a single 1 inside, but now we want to have an odd number of ones. And Lucas, you just sandwiched it between 2 even numbers of ones. So I think that that's a good idea, right? Because in that case, So if we have this as like the beginning of our regular expression, then we'll be, well, I guess we're not requiring that we start with a 1 in this case, right? Sean, I think your idea, you can't generate an infinite amount of 1s. So Sean, with yours, you can only have, and Sean, it's not even odd, unfortunately. Yeah. Okay, so Luan, you sandwiched a single one between 2 evens. Let's see if, oh, I'm sorry, wait, who was that did that? That was Lucas. Okay, so Lucas, what if we just sort of popped something else at the end? So David, the problem with yours is you can't have a pair of 1s with an arbitrary number of 0s in the middle. Does that make sense, David? No, okay. So in yours, you can't have an arbitrary number of 0s between 2 1s. You can't have, for example, here, let me write it out. You can't have, well, even this one. Well, now let's do a better one. You can't have 1 0 0 0 0. Oops, sorry. 1 1 0 0 0 0 1. This one should be in the language, but David, it's not in your language. Does that make sense? It is. Okay, what if I, yeah, you have that 0 star in the or. I'm still suspicious, though. I'm worried that your 1s are too close together, David. That's my problem. So let's see if I can find a counter example to David's. And Luan, I think you have the right answer, but before we get to that, you need a 1 1 star. Okay, that could be. But I'm worried about, here, let's try this. What if we have, well, maybe it does work. Maybe I'm wrong. I was worried, but maybe I shouldn't be worried. So that's what I'm worried about, right? I guess for that, you would have 1 0 0. Yeah, so David, I think this one is not in there. Yeah, but if you started with a 1 or empty, then you wouldn't be guaranteed to have an odd number of 1s. Right? I definitely don't think you should have a 1 or empty in here because you're not guaranteeing the odd number of 1s in that case. Yeah. So I think we should go with Luan's, right? I think that's the right idea here, which was after this guy, we put a 1 0 star 1 quantity star. Does that guy make sense? Right? Because you have the first one, and then this makes an even number of 1s, right? But I think the problem with this is that you would need to have more 0s before or after the 1. Yeah, I agree. Yeah, that one seems good. Yeah, exactly. Because you need to have 0s here with stars, right? So we would have 0 star, 1 0 star. And then in here, 0 star, 1 0 star, 1 0 star, quantity star. Yeah, I think that one's right. And that's what I was saying about when I was arguing with David's, right? Is that I was worried that the 1s were glued together, right? And there wasn't this sort of 0 star as a buffer between them. Yeah. Yep. Yeah, these get interesting, right? Yeah, fun. These are cute little puzzles, right? All right. So let's leave these in the dust and do something completely different. And as we're going to see next week, they're actually exactly the same, but it's going to look very different at first. Okay. That's why this is so fun, I think, because you have these two totally different mathematical structures that you build, but then it turns out they're actually exactly the same. It's kind of fun. So we talked about regular expressions. Next, we're going to talk about finite automata. Automata. Okay. Now, a finite automata has 5 parts. Okay. Maybe I should do, let me do a script now. I already messed it up. Let me do a script A. Okay. 5 parts. I, S, S0, A, and N. Here are the 5 parts of my automata. I'm going to go through each one of these and explain what they mean. Okay. So I is called the input alphabet. S is the set of states. S0, that's a lowercase s. S0 is the starting state. Okay. A is the set of accepting states. And N is the next state function. Okay. And to talk about this, I think we should do an example. Okay. So I'm going to draw you a picture. And what I'm going to do is go through and describe these 5 parts for the picture. So here goes. Here's my picture. And it's going to be a little bit like an arrow diagram, but it's going to be, we'll put it this way. It's like a directed graph. I think that's the best way of putting it. So these are going to be the vertices of our graph, and then we're going to have edges between them, but the edges will be labeled arrows. Okay. So here's what my arrows are going to look like. I'll have a 0 arrow and a 1 arrow coming out of state S0. I'll have a 0 arrow and a 1 arrow coming out of S1. And then I'll have a 0 arrow and a 1 arrow coming out of S2. And here's my finite automaton. Okay. So in this case, my input alphabet is going to be the set 0, 1. The input alphabet are the different labels on my arrows. Okay. And since I have 0s and 1s that are labeling my arrows, that's my input alphabet. What do you think the set of states is going to be in this example? I forgot a little piece. Any idea what the set of states would be? Okay, I'll help. No, not 0, 1. It's the circles, S0, S1, and S2. My starting state is going to be S0, as it's described here. The accepting states are indicated by the double circle. So S2 is the only accepting state. And the next state function is going to be described by a table. Okay. So here we're going to have a little table where we have our state here and our input here. And I think you guys might be able to do this part. See if you guys can fill out this table. Right? So from S0, on the 0 arrow, what is the next state that I go to, according to this diagram? Not 0, not quite. You're going along the 0 arrow, but you end up at S1. That's right. How about from S0 going down the 1 arrow? S0, nice. That's this one right here. We're starting at S0, reading a 1, which takes us back to the same state as 0. Okay, how about S1 reading a 0? Where are we going to go? S1, good. About S1 reading a 1. Where do we go? S2, okay. About S2 reading a 0. Where do we go? S1. Finally, S2 reading a 1. S0, very nice. Okay. Let's do another example, and I'll let you guys tell me all the different parts, right? So let's look at, let's look at one of these guys here. Okay, so here's my picture, and I'll just read the things off to you. What is the input alphabet going to be for this finite automaton? Almost A, B, C, right? So we got some C's in here as well. Nice. Okay. What is the set of states? U, V, Y, Z, or U, V, Z, Y, either way. Good. What's the starting state? I'll give you a hint. It's the one that an arrow points at that comes from nowhere. Yeah, U. U is the starting state because it has an arrow pointing at it from nowhere. In mine, I drew it a little bit differently. Here, my starting state was S0. I didn't put the little tail on it, right? The shaft of the arrow I didn't put in. You can draw it either way. You can draw it with the shaft, without the shaft. I just draw a little greater than sign for my starting state, but it's up to you how you want to draw it. Okay. What are the accepting states? V and Z, those are the ones with the double circles. Good. Okay, so that's the set of accepting states. And finally, if we were going to do a transition function here, right, let's just go state by state and talk about all the transitions. So for U, which states are you going to go to on an A, B, or C? So just put them in order for A, B, and C. So from state U, what 3 states do you visit traveling on the A, B, and C arrows? Z, Y, and Y, right? Z for A, Y for B, and Y for C. Okay, how about state V? Where do you go for A, B, and C? V. V for all 3 of them, right? From state V, you always go back to yourself, no matter what you're reading. V, it turns out, is a trap, okay? How about state Y? Where do you go for transition arrows A, B, and C? Sometimes traps are accepting states and sometimes they're not. In this particular example, we've set up the book rather has set up the traps to be accepting. Sometimes they're not. Just depends on the automaton, right? Yeah, great question. Okay, so what are our transitions from Y for A, B, and C? Z, V, Y, very good. On A, we go to Z. On B, we go to V. On C, we go to Y. And lastly, Z on any input goes to itself. So that's our transition function. Okay. There are some similarities between regular expressions and finite automata, in that the purpose of a finite automata is to define a language. Okay? The way that you define a language in a finite automata is that you have a string, and your string is made of the same input alphabet as the string alphabet is the same as your input alphabet. So for this example, we would have a string of ones and zeros. So let's consider the string 0, 1, 1, 0, 1. Okay. So on this string, we're going to travel around our automaton. And the way that that works is we start at the starting state, as you would think, right? And for each letter in our string, we're going to follow one arrow, okay? So let's trace through it. Starting from 0 in the start state, where do we go next? Okay, I've lost you. Okay, so starting in the start state, reading a 0. Oh, you put in the whole answer. Okay, well, sweet. Reading a 0, we follow the 0 arrow down, which lands us in S1. Then we move on. Here, let me switch here. Then we move on to the next symbol, which is a 1. And so from S1, we take the 1 arrow, which takes us down to S2. And we have another 1 here. Well, now we're going to read this 1 to bring us back to S0. And another 0 takes us to S1. And finally, another 1. You almost had it, David. The last one should be an S2. But other than that, you're right. So this string, almost there, right? This string is an element of the language, because it's after you're done traveling around the automaton, you end up in an accepting state. An accepting state means the string that you were traveling with, right, traveling for, that dictated the route of your travel, lands you in an accepting state. That means your string is in the language. Okay, so let's do another example. How about 0, 0, 1, 1, 0, 0. Let's do that one. Okay, so if you just list out, a 0, 1, or 2, let's see which states you go. So you start in state 0. Where do we go next? S1, okay? And from S1, now we're on this symbol, where do you go next? Still S1, good. Then on a 1, where do you go next? S2, okay? Reading another 1, where do we go next? Back to S0, good. Reading a 0, where do we go next? S1, good. And finally, our last 0, S1. Is this string in the language if we end up in state S1? No, good. Why not? How come this string was in the language? Yep, because we have to end at an accepting state, which has the double circle, and this only has a regular circle. So this is not in the language. What do you guys think? Should we do one more example? Well, let me ask you some questions. Okay. Someone give me a string that's accepted by the automaton. And then we'll trace through it. So you guys give me an accepted string. 0, 1. Okay, that's a good one. 0, 1. Okay, that works. How about a longer accepted string? Okay, a bunch of zeros and then a 1, because we would go 0, then 0, 0, 0, 0, 0 would just sort of loop around in S1 for a while, and then the 1 at the end takes us to acceptance. Excellent. Okay, how about a string that's not accepted by the language? Okay, any number of ones, 1 star. So I love your use of star there, Luan. That's perfect. Okay? So we have a bunch of ones, doesn't matter how many. We could have none of them, 10 of them, a million of them. No matter what, we're just going to keep looping around in S0, which is not an accepting state. Okay. Also, 1 star 0 doesn't get us accepted. You can loop it here as much as you want. That doesn't work. All right. 1 star 0 star also doesn't work. Those are all not accepted strings. So Luan, that was great. Yeah, I really like your usage of the star there. Star and concatenation, right? Nice. Okay. Last question. See if you can describe in English the strings that are accepted by this automaton. Just like we were doing with the regexes before, right? Same question, different mathematical object, right? Someone describe in English the strings that are accepted versus the ones that are not.
Something like as many ones as you want, as many zeros, at least 1 0, and then as many zeros as you want, and it must end in a 1.
Very close. So ending in a 1 was on the right track. Lucas, you've got it. Any string that ends in 0, 1. See why? Because you can loop as many ones, as many zeros. You could have a 0, 1, that's fine, so long as you do a 1 to get back, right? But if you have a 1, then you have, and you want to end in 0, 1, you have a 1 on there. You can't have a 1, 1, right? A 1, 1 at the end of your string means you're not accepted. A 1, 0 at the end of your string means you're not accepted. But if you have anything, right, you're in any state you want, and you have a 0, 1, you're going to be accepted. Let's look at that. If you're in S0 and you have a 0, 1, that'll take you here, 0, 1. If you're in S1 and you have a 0, 1, you're good. If you're in S2 and you have a 0, 1, you're good, right? So Sean, that's exactly right. It's as though you have 1 star, well, not quite. Okay, so Lucas, it's going to get easier. These are actually easier than the regexes. You just need a little more practice. I promise it'll get easier, right? The regexes are actually the harder one. So Sean, that's a whole nother question that we're going to consider next week, is how to take one of these and transform it into a regular expression. Also, we can take a regular expression and transform it into one of these, right? And that's what we're going to work on next week. Right? But for now, we'll just stick with the English descriptions, right? So let's do another example, right? Let's do that example from your book where we had this guy here. I'll put this up here, actually, this way. Oop, oop, oop. Let me zoom in a little. Oh boy. Okay. So on this machine, let's think about some strings and where they're going to go. Okay. So let's say we have, A, B, oops, I'm a little tall here. A, B, A, B, A, C. And let's see where we're going to go. There. Now we can see. You can almost see. Okay. Perfect. So let's work through the states where we're going to go to. Okay, so which state are we going to start in? I'm going to use this one on the left. So which state do we start in here? U, perfect. Okay, reading in A, where do we go next? Z, good. And then a B. And we get trapped there. Very good. So if we read an A at the beginning, we get trapped. And is that string here going to be accepted by the automaton? Yes, because we're trapped in an accept state. Very good. So this one is in the language. Okay. How about someone give me a string where we get trapped in V and therefore are accepted by the language? Someone give me a string like that. So I want a string that gets trapped in V and therefore accepted. Okay, BB, and then anything you want. So any string that starts with BB is going to be accepted, right? Okay. How about a string that's not accepted? So here we have B, B, A or B or C star is in the language. Okay. Okay, B or C, C star is not accepted. B or C, because we can take either the B line or the C line. And no matter what, if we stay here with C's, C star, we're going to not be in the language. Okay, very nice. So same question as before. Can you describe to me what language is represented by this automaton in English? Okay, any string that starts with A or BB or CB or BA or CA. That's a pretty big list. Okay, so let's see if we can sort of pare that down. Let's see if we can make that a little bit more efficient, right? If it starts with B or C, it can't end with C. So David, that's true. So Sean, yep, no, it's not true. Nope, I take it back. Sean, you've given a counter example, right? And David, in general, you don't want to say what it can't do because we're trying to describe the accepting language rather than the rejecting language, right? So if we were trying to describe the rejecting language, your answer would have been in the right vein, right? But since we're trying to talk about acceptance, it's sort of going the wrong direction, if that makes sense, right? So can we come up with, yep, okay. So can we come up with a little bit more concise description here? Let's do it in two parts, because you can be accepted here or you can be accepted here, right? So I'm not quite sure what you're getting at there, Sean. Would you say it in English instead?
So I was trying to. I think my parentheses are pretty big there. So it has to start with A, or it can start with B or C followed by an A or B, and then at the end there should be like an A, B, or C star, because then it can end with whatever. It just accepting depends on what the two starting characters are.
Well, not necessarily though, right? Because you could have B and then a bunch of C's.
Oh,
right?
and then finish it off with something that gets you out of that loop.
Yeah,
Right.
exactly. Right. Okay, so Lucas, I think you're on the right track. Any string with an A, two B's, or B and C. Well, I agree with the first two, but not the third one. I think the first two you would have it. It's any string that has at least at least one A, or at least two B's, right? If you have a B and a C, that doesn't help you. You're still in a reject state, right? So the English description would be C before. Oh, or oh, I see. Or CB, right? Good. So I see what you're getting at now. So there's three ways to get accepted. You could have a single A anywhere in the string. You could have a single B, pardon me, you could have two B's anywhere in the string, or you could have a C followed by a B anywhere in the string. And in those three cases, you're guaranteed to get to one of these except state traps. What do you guys think? Does that make sense? Let's try the other one. Let's see if I can. Whoop. That's really hard to. Here, let me do it that way. There we go. Okay. So what about this guy? And how would you describe that guy in English? So the first part is similar to the last one, right? How do you get trapped in Z? So to get trapped in Z, what do you have to have in your string? Start with an A, or B and C and then an A. So let me make that a little bit more concise. If you have an A in your string, you're accepted, right? If you have at least one A in your string anywhere you want, right, you're going to be accepted, right? So if you're here and you have an A, you're accepted. If you're here, you have an A, you're accepted. If you're here and have an A, you're accepted. And if you're here, you have an A, you're accepted. So and no matter what, if you have an A, you're accepted. Okay. What about the other letters? How do the rest of them work? Double B's are accepted. Good, because we can still go BB, right? And that'll get you there. Okay. And what else? C, then anything, then C. I would say C, then anything except C, right? Yep, then A or B. Yeah, exactly, right? These two are supposed to be the same machine. Anyone notice that? It's just two different ways of drawing the arrows. See, here we have a separate arrow for A, B, and C. And here we just have one arrow and we just separate those with commas. These are actually identical. See how that works? Here we have two different arrows for B and C. Here we just have a comma, right? Same thing up here on the V state. Here we have separate ones. Here they're the same. Looks like it doesn't need four states to be the same. That could be. Yeah, it's just like it's possible to have shorter and longer regular expressions that pick out the same language. In the same way, you can have more or less complex finite automata that accept the same language. So maybe you could reduce this down to 3 states. That's possible. Yep, you could delete state V and point the B arrow at Z instead. Absolutely. And that would be the same machine, right? In that it would accept the same language of A's, B's, and C's. Okay. So what we've done is we've taken a finite automaton and described the language that it accepts using English. Okay. Now what I'd like to do is go the other direction. Now I'd like to describe a language of strings in English and draw a finite automaton that accepts that language. We've got some examples here. So let's do an odd number of ones. That's one that we left off with last time, right? Our odd number of ones. Let's make a finite automaton that accepts that same language. You start to see this sort of connection between the regexes and the automata. Oh, by the way, singular automaton, plural automata, right? So finite automata, right? If you had just one, it would be an automaton. That's singular. Right? Okay, so let's build, and I'll just show it to you, right? So to build an automaton, here's what we're going to do. We're going to have, we're going to try to accept an odd number of ones in our string with our input alphabet of 0 and 1. Okay, so I'm going to start off in a state, right? And this is for the empty string. I haven't read anything yet. Now, if I'm trying to have an odd number of ones, is my starting state going to be accepting or rejecting? Remember, this is for that represents I'm starting with the empty string. That'd be rejecting because I haven't seen any ones yet. So if I want to go over to an accepting state, like this, what's the label on my transition going to be? 1, right? Okay. And once I'm accepted, I have an odd number of ones. How could I go back to my rejected state? So here I have an odd number of ones, right? So to go back to rejected, I have to read another number 1, which would make it an even number of ones, because over here I have odd. If I see another one, I'll go back to even, right? What about zeros? What if I start off and I read a 0? Am I still going to be rejected or am I going to be accepted? Zeros are just loops. If I have an even number of ones, like the empty string, for example, and I read a 0, I'm still rejected. If I have an odd number of ones and I read a 0, I'm still accepted. And there's a finite automaton that recognizes that same language of an odd number of ones. Here's the regex that does it. Here's the automaton that does it. What do you guys think? Does this guy make sense? You happy with that? Questions? Yep. We can label these if we want. Let's label these states even and odd. Why not? You can call them S0 and S1, but that's not a very good description for your variable, right? Better description is just to put words in here that actually describe what the heck's happening, right? Okay. So let's try this. Let's try a string that doesn't have 2 1s in it. Okay. So what do you guys think? Our start state. Is that going to be an accepting state or a rejecting state? When we haven't seen anything yet, just the empty string. Accepting, right? So here, I'll make this an accepting state. Okay, that's when we've read no ones. Okay, what if we read a single 1? is that going to be accepting or rejecting? Accepting. So this will be, we've seen 1, 1. Let's put the zeros on here. If I'm in my start state and I read a 0, where should I go? Loops on both. Very nice. Because these states are just counting how many 1s I've seen, right? So here I can see as many 0s as I want. It doesn't change anything because the number of 0s is not what's described for our description, right? If I've seen a 1 and then I see some 0s, well, I've still just seen a single 1, right? Well, what if I see another 1 and I go to a state where now I've seen 2 1s? Would this be accepting or rejecting? Not exactly, Sean. Okay, so this one will be rejecting, and it will have a loop for 0. What do you want? Maybe I'm misunderstanding. So if you see 2 1s, that's obviously rejecting. That's the whole idea, right? Doesn't have 2 1s, right? So if we've seen 1, 1 with some 0s in between on the loops, right? And we get here, well, then that should be rejecting. And if we see some more 0s in that state, well, that doesn't change anything, right? Are we done? No. Okay, why not? Exactly 2 1s. Yeah, not more 2 or more, but it doesn't have exactly 2 1s. Yeah, it could have 3 1s, and that's okay. We could have 10 1s, and that's okay. We don't want to loop back. Why not? We don't want to take our 1 arrow and loop it back to here. Why not? Okay, we want to go to a new accepting state that has 2 loops on it. The reason why we don't want to take our 1 arrow out of here and come back is because what if we had a string with 4 1s? Then we would go, it should be accepted because it doesn't have 2 1s, it has 4 of them. So let's see what would happen. We would go first one, second one, third one, fourth one, right? And then we would be rejected even though we should have been accepted. So instead, we'll go to a final accept state that, as Sean said, 3 or more, greater than equal to 3, I'll label it that, and it's an accept state, right? And here, it's going to loop with 0 or 1. After 2 1s, you can do anything except a string of 0s. That's right. And you can tell that you weren't done because every state has to have an arrow coming out for every letter in the input alphabet. You see, every state has a 0 coming out and a 1 coming out. There's no restrictions on what's coming in, right? Here we happen to have a 1 coming in and a 0 coming in. That doesn't matter. It only matters what's leaving, right? So here we have a 0 leaving and a 1 leaving, so this state's good. 0 leaving and 1 leaving, this state's good. 0 leaving, and before there wasn't a 1 leaving, so we knew that we weren't done yet. Once we put in the 1 leaving and decided where it went, then we're okay on this state. But now since we went to a new one, this has to have a 0 and a 1 leaving as well. What do you guys think? Good? Got it. How do you indicate the string cannot be valid no matter what happens next? Then you go into a trap that's not an accept state, right? So sort of like the ones in the book, right? Where you went, let's say that you have, let's do one more example in the final minute that we have here, right? So less than 2 1s. Okay, so for this one, we'll start off accepting with 0 1s. This one will also be accepting for 1, 1, a single 1. There's my 0, there's my 0. But for this one, we're going to go into a reject state greater than or equal to 2, right? And this has a loop on it for 0 or 1. Does this make sense? Yes, that's what we're going to talk about next week. It turns out that any finite automaton can be transformed into a regular expression, and any regular expression can be transformed into a finite automaton. That's next week's material. Yeah, cool. And we'll do a bunch more practice of both of those along the way. It's quite a nifty proof. It's going to take pretty much the entire class time. It's quite extensive, right? So again, we don't have lab this week. I think we're just not going to have any more labs this term. We're just running so short on time that I'm just trying to make it through all the material. So yeah, so you can forget about the lab this week. And next week is right before finals, so I'll give you a practice final, and you'll be working on that. So yeah, so don't worry about the labs this week or next week. Yeah, cool. Okay, any other questions for me before we go? All right, well, I hope you enjoyed this one today. This is some of my favorite stuff, so I hope you liked it, and we'll expand upon it quite a bit next Wednesday. Remember, we do not have class on Monday. It's Memorial Day, so enjoy your long weekend. Get caught up on any work you need to do, and we'll have one more good class next week. See you then. Bye, guys.